Today's topic uh, is about strain. Strain. So we need to understand the definition of strain. Okay. Today's topic is strain. Strain is the second chapter, chapter two of the book. Even I have passed to you the lectures, but it's more convenient for me to elaborate or explain to you on on the textbook. Okay, so you can follow the textbook. Atwan and follow textbook. Okay, khotam kan la khotam. Ama textbook hi khomana. O inardum bo yana ama textbook okay kanardum botan. You can follow on this textbook. The time be kan la khotan o away min basiakam. David la khotan yan hala sar away khom away staibin. Okay, chapter 2 and second chapter. So the first thing, the chapter is about strain. So you need to understand the definition, what strain is about. Okay, strain, basically strain has to do with deformation or deformation. Okay, deformation or deformation. If you have a rubber band like this one, rubber band, okay, and then you draw these lines. You have a line that is along the vertical axis, okay, this is, you could say, is along the y-axis, and you have a line that is along the horizontal axis, okay, the x-axis, and a diagonal line, okay, a diagonal line segment. So you have 1, 2, 3 lines. You have 3 lines, but focus on the vertical and horizontal. If I apply a force, a rubber band would take only a tensile force. It wouldn't be able to take a compressive because it's rubber. Rubber يعني هنا لاستيقي في هنا. So a rubber band can only take a tensile force. So if I apply a tensile force on this side, after the tensile force has been applied, you could see the rubber band. You see the deformation is quite clear in the rubber band. Okay, you can feel that the rubber band over here is wider than the rubber band over here, right? You can notice that rubber band on the left side is wider, has the width is more than the rubber band on the right side. Why? Because we have applied a tensile force. So after the application of the tensile force, you could see that the rubber band has elongated, okay, elongated. So that means the rubber band, after applying the tensile force, we have changed its length, okay, increased its length, okay. So so it has experienced elongation. If we pay attention to the vertical line, so what kind of deformation the vertical line would experience if I apply a tensile force to the rubber band? What kind of deformation the line would experience? And if any one of you could tell me what kind of deformation? Deformation, any change in length. Change in length, okay? Deformation, any change in length. Okay, what kind of deformation the vertical line would experience if a tensile force is applied to this rubber band? You can see this rubber band is attached to at its both ends, okay, this side A, B. If you pull this rubber band apart from each other, okay, Deniz, yeah?
أستاذ لينكسك زيادة لبي يعني فورمشتك زيادة.
Yeah, exactly. Increase in length. This line has experienced increase in length due to the tensile. Okay, who could tell me what the horizontal line, the x-axis, or the line along the x-axis, what kind of deformation this line would experience, other than Deniz, someone else. Someone else who could reply this question, who could answer this question. We have a line along the horizontal. Bina. Bina. Yeah. So that means this line would experience shortening. This line experience shortening. Okay, the horizontal line experience shortening. So that means once you apply a tensile force to this rubber band, based on what you can see over here, the line, the vertical has elongated, while the vertical elongated and the horizontal shortened. Okay, so two effects. We've seen two effects. How about a line that falls in between the vertical and horizontal? How about the diagonal? If we have a diagonal line segment, a diagonal line segment like this one, which falls in between the vertical and the horizontal axis. So can we, yeah? Who is this? Asrin? Okay. Asrin said the diagonal would keep its shape and length and everything. There will be no change happening to the diagonal. Who would agree and who would disagree with Asrin Desco?
Well, I disagree because.
You disagree. Give me a reason. Defend yourself. Why do you disagree?
Because there's like a force or a stress on an object. Like it's kind of impossible to say that there will be no deformation. So I disagree, and I think it will change its shape. And since we are not working on it directly, it might kind of be crippled. You know, the shape could be crippled because we are not working on it directly. Yes.
Okay, but just Yahya, explain it in a firm way. Don't say that I think because there's a force and there would be change in shape. You could see now you have a vertical and a horizontal axis, right? A vertical and a horizontal. This is to all. It doesn't mean that Yahya has to explain it to me. So someone else could tell me the reason nicely on why the diagonal, there would be some change in the diagonal, or there would be no change, as Asrin said. Asrin Desco said there would be no change in the diagonal line. Yahya says, well, I think there would be some change because we have applied a force, definitely, which is, he's not giving a good justification, even though he is saying that we have applied force. Everybody knows, even Asrin, she knows we have applied a force, but give me the exact reason if there is a change, and why would a change take place with this diagonal line, and why, if there is no change, why there would be no change with the diagonal line. Bahra, bale.
ئەگۆڕێ مامۆستا چونکە بەڕای من گۆشەکەی دەگۆڕێ یعنی ڕۆتێتی دەکەوێتەوە.
گۆشەکەی دەگۆڕێ. Okay, this is another answer, which is a bit better than, not to say better than Yahya's answer, but still not the exact good answer that I'm waiting for. Someone else? Bina, okay, Bina.
Ustaz, اگه horizontal length'eke بگوره vertical'ekش بگوره incline'ekش خالکان دگوره تا دیویش دگوره.
That is the exact answer that I was waiting for.
يعني x و y که دگوره.
Yep, that is what I was waiting for.
horizontal.
Okay, that's what I was exactly waiting for. The horizontal and the vertical, if they both experience changes in length, regardless expanding or contracting, that means increment or decrement or increase or decrease in length. So definitely the diagonal line would experience the same amount of increment on the y-axis, because the projection, if I draw it for you, if this is the y, okay, if this is the y, okay, if we have an increment in the y, so definitely this component, the y component of the diagonal, increases with the y-axis, increases, because the initial projection, how to say, this is the projection, so if this is the original, let's say this is the original diagonal line, and we have y and we have x, okay, this is the x and y. So then afterwards, so this is the initial projection of the diagonal line. This is the initial projection of the diagonal on the y, and the x, on the y and the x. Okay, if we have, this is the projection on the x-axis. So you see, the projection means like the reflection of the diagonal line on the what do you call, on the x and y. Okay, the projection is you project the diagonal, it has a projection on the y and x-axis. So the projection means the component. We have two components, and out of these components you can construct this diagonal. So if this is the original component, the along the y and the x, so definitely if there is some increase or decrease in the y or in the x, this would also affect the diagonal length. And then if we look at this new after change in length, for example, if it has increased in the y, so definitely the projection would increase. And if it has decreased in the x, okay, a decrease in the x, so you could see that the diagonal has changed its length, right? It changes its length because it has two components along the y and x. So due to these two changes, okay, even if the change is just along the y, for example, though it's along the x and y, we cannot ignore the x-axis. But in case, for example, if only the changes along the y, which is not possible to have one change along the y, it has to be along the y and x, because if you imagine it, that if the increase takes place along the y, so surely the x has to be contracted. So there must be a decrease in the x-axis for the diagonal to meet the, to be at the meeting point between the projection of the x and y. Because we have two projections, one along the x-axis and one along the y-axis. This is the projection of the inclined line or the diagonal line, and this is the projection. This is the projection of the diagonal line over the x-axis. Okay, so there would be a change, and that was a good explanation from Bina about how the diagonal would behave when we apply a tensile force on the rubber band. Okay, so this is correct. Okay, so now we've come to the fact that we understand what deformation is and how a deformation takes place. So when we apply a tensile force, there will be some increase along the y-axis or along the vertical line, and there will be some decrease along the x-axis. So surely this would affect the diagonal line. And in case if like this was not a rubber band, in case if this was like a steel bar, okay, and then we have these two lines, the x and y, okay, along the vertical and horizontal line. And again, we have this diagonal line. So when you apply a compressive force, this time, this is a steel bar, okay? I have changed the material from rubber band into a steel bar, because rubber band cannot take a compressive force. So if now we apply a compressive force, okay? If now we apply a compressive force to this element, and this element is steel. Steel could take a compressive force. So what kind of change would you expect with the y and x-axis, or with the line along y and x-axis and the diagonal as well? What kind of changes?
يعني vertical decrease the
Just raise your hand so I pick you up, then you answer. This is
Sorry.
the way it works, okay? Because you have answered me previously, so I would like to pick up someone else to answer this question. Gila, okay. Gila.
منصة جراعة واي كم دكات اكسكا زيادة كان.
Exactly. If you apply a compressive force, then the y would get shortened. The y would get shortened while the x would get extended. Okay, lengthened. Okay, increase the length. Okay, so you shorten along the y and increase along the x. So these two effects along the y and x, would it affect the diagonal? Would it affect the diagonal? Would it affect the increment in the x and the increase in the y along the y? Would it affect the diagonal line? Would it affect it? Yes, it would affect the way the rubber band, the change in the rubber band has affected, though it was increment along the y and decrement or decrease along the x, it has an effect on the diagonal. The same thing is applied to the diagonal again, but this time the reverse order. Instead of having a decrease in the x, you're gonna have increase in the x, and instead of having increment along the y, you're gonna have a decrease along the y, or shortening along the y-axis. Okay, now we fully understand these the concept of deformation and how deformation takes place. Okay, so is it necessarily for deformation to take place only when you apply a force? This is the only way we could apply deformation? This is the only way we could apply? Is like you have a tensile force or a compressive force on the element, then the element would experience deformation? That's the only way to get it, or there are some other ways to get the element deformed? Any idea? Any idea? If you have any idea, let me know. If not,
أستاذ بسوراني جو بزانم أو إذا قوري.
okay, just raise your hand so I pick you up, whoever you are.
هذا أستاذ. بسوراني ديفورميشن إذا قوري يعني.
بشي سوران؟
هذا روتيني يعني بايب.
By the day, no. لا ما بس مأونية ساعة أو وتمان you apply a force. So now if there's any other ways سوران إما بس ما نكردوها أي سورانين يعني we apply a force. This is one method. سوران نوتشية يعني ساعة ما بس أما change in position يعني why they become length ثانية أقوله؟ لا شتواني.
بدو أراسي جواز بايب دي مثلا هر سنة كان بدو أراسي جواز بايب دي ناقورة أوكي deformation نابي.
أويش هر tension و compression عينشته هر force أويش عينشته. أنا أونيا. Wrong answer. Okay, anyone else? Anyone else? Who else? No. Ramya?
أستاذ نتوانين بلاي جيرمي temperature deformation بسرداني.
Yep. So change in temperature. If any change could take place in temperature, be it increment, you change it, increase the temperature, or decrease the temperature. So you elevate or lower the temperature. That means you either make it, either you increase the temperature, you heat it up, okay, or you cool it down. Either way, you can change because materials get expanded when it get exposed to higher temperature, and it get contracted when it get exposed to lower temperature. Okay, so due to that, we also can, the material can experience, in fact, deformation due to either you exert forces or you change the temperature, the temperature, okay? Either you increase it or decrease the temperature, then the material would either expand or contract, okay? So that is another way to experience deformation. So now we understand, fully understand what deformation is, how deformation takes place, why would it take place, and why would it be increase or decrease. Okay, we know all these things. That now we go into something else called strain, the concept of strain. Once we have defined the concept of deformation, we can now understand what strain is. Strain is, in fact, strain is just a dimensionless, a unitless or dimensionless kind of deformation. So the definition of strain, which is epsilon, symbolically we represent strain by an epsilon, this epsilon, okay, epsilon, and then we equate epsilon into delta L, erase it. Okay, delta L over L, okay, change in length over L. So this is strain, doesn't look like a nice epsilon, make it nice, which is not so nice. Anyway, so this is epsilon equated to or equal to delta L over L. Okay, if we have an element like this one, you can see this one, okay, and then we have a tensile force at both ends, okay, so the element is experiencing elongation. So this is the original length of the element prior to applying the load, okay, prior applying the load, the element length or the original length, L sub naught, is the original length. So we could say this is L sub naught. Okay, once you apply a force, a tensile force, then there would be, the element would experience some sort of deformation, and that deformation would be elongation, increase along the x-axis. Okay, this is the line segment, the length, the new length. You could say this is a new length. We label it as L prime, new length. This is the original length, okay? This is the original. Prior to load application, we call it original length. After load application, that after you have exerted a tensile load on the element, okay, you're gonna get a new length. So that means what is meant by change of length is neither the original nor the new length. It means the difference between, for example, it has experienced elongation, so we could say elongation minus the original length would be equal to change of length, would be equal or represent change of length. So that delta L means that L prime, the new length that you've got after applying the force along the element, okay, and you subtract from the new length its original length, the element had prior to the load application over the original length. So we have this original length prior to load application. We have it, and we have this. The only thing that you need to get is the new length. Once you have calculated the new length, then you can get delta L over L naught. Delta L over L naught. So someone else might ask me, how about if we apply a compressive force instead of having this P, okay, not instead of having P, instead of having a tensile force, we replace it with a compressive force. We just replace it with a compressive force. So we just change the direction of the load application. So instead of having a tensile, I apply a compressive on the element. I apply a compressive force on the element at its both ends. Okay, so after applying a compressive force at both of its ends, you're gonna get what? If this is the how to say, this is the original length, L sub naught. So the new length would be less than the original length. So instead of having expansion or elongation or increase in length, you're going to have decrease in length. So if this was the original length, okay, if this is the original, so after applying the force, you're going to get this much of the length. Okay, so that has increased, the force has increased the length. So this would be your delta L, your L prime. So the same, you apply the same thing to get this strain. You're going to get the same. You're going to apply, the same law or formula, whatever you call it. Okay, L prime. Then you subtract. It doesn't matter, negative or positive, because at the end, what I need is change in length. What I need is this change in length. That's what I need to get. So be it positive or negative, I don't care about the sign. The sign only tells me if the the length has increased or decreased. That's all what I get from the sign. Okay, so if I like L prime minus L, and I've got like negative, I surely know that this means the new length is less than the original, so there must be some contraction. So the negative would tell me what? Would tell me that some contraction has taken place in the length due to the applied load. But if I get a positive, like this, the first example where there was a tensile force, if I get a positive sign, then that means some elongation or increase in the original length has taken place within the element length. That's why we've got a positive sign that would indicate to elongation rather than decrease in the length. And that wouldn't change the strain. The strain still is a dimensionless, is a dimensionless character, and we have to get the delta L, which means change in length over the original length. So from this, you can get the change in length divided by the original length, and you're going to get the strain. Okay, you're going to get the strain of that element after applying the load. So this is the concept of strain. This type of strain is called specifically, if we label it as normal strain. Normal strain. Okay, normal strain. Okay, and it's indicated too also as an average normal strain. Average normal strain. Okay, average normal strain. Okay, average normal strain. Okay, average normal strain. Either you say normal strain or average, but because we're going to study something else which is called shear strain, that's why to differentiate between the normal strain, so you have to specify it as normal strain, the other one as shear strain. We have another type of strain called shear strain. Okay, so is it clear enough? The normal strain, be it in tension or compression, we will get something called normal strain, which the formula of the normal strain, you don't need to memorize anything. All what you need to memorize is to know that strain has to do with change in length over original length. Change in length, which means delta L over L. Delta L over L over L. Delta L means this, delta, change in length. How can we get this delta? Mathematically, you